Hello there. Welcome back. I'm on, I don't even know what episode, and it's evening because I kept having to unpause and pause the game standing right here, breaking this flower to get my sound properly to work. Yeah, it's been a while. So, in real life, I did some gymnastics today, and I'm really tired because I've been flipping and conditioning and doing all sorts of stuff. But it's probably healthy. It's probably good. Basically, just from dieting, I lost about 10 pounds in the last week, and exercise should help me out a little bit. Um, school, school. Taking 3 math classes. Did pretty well this entire semester up until now. I have lost a little bit of motivation. It's probably why I'm playing right now. I know that this is East. So yeah, for anyone who hasn't seen, I don't think I posted any episodes of this since I thought I quit forever, but I think I posted since my good old Star Wars video that got me 2,000 subscribers pretty much. So the deal is I have this series. What am I looking at? Block. Okay, yeah. I have this series where my job. What do we have in the? I just want to check. My job is to just keep heading east in Minecraft in single player. That is that's my job, or that's what I'm doing. Oh yeah, I have a lot of stuff. Gold. I don't remember why I need gold. Blaze rods, block of irons, and we are gonna play in the updates. I'm pretty sure. So yeah. Although I'm not connected to the internet, and it does say 1.8.9, so actually I can't remember if 1.9 came out. The combat update was that 1.9? Yeah, but I'm not playing in that yet, so yeah, we can enchant stuff. We need a new sword sometime soon. Yeah. See, Minecraft it seems fun. Like if you haven't played it in a while, it gets old. Like if you play it way too much, I don't know. It depends. Like you can get really into it. And yes, what stinks is I still have to play in in a windowed version. I can't play full screen because QuickTime is kind of frustrating in the fact that it doesn't really provide me like whatever. It doesn't okay, what do I say? QuickTime doesn't let me record full screen in a low resolution lower than the actual screen resolution, which is bad because I don't want to. I have like a big screen and it's a high resolution, and I can't record that long in that much resolution. It's too much memory. It's too much processing. It's just not good. And this is also not good. There's a lot of, and I haven't slept in a bed that I remember since who knows when. So I should probably sleep in a bed. And that's something I remember. I think I put the beds at 0, 0. Or at z equals 0. Because reasons. Because it's easier to find. If I need to go back and if I drop a chest or something, it's just easier if everything's at 0, I can find it. I never have to worry about things getting lost, because I just follow that like a straight line, and I basically don't place like valuable things or beds or anything like outside of that line. Just if I ever need to find them. for whatever reason. Not that it's that important to find a bed, I guess. Because the whole point of a bed is, you know, I guess it's more important that I can find my stuff. Like if I die, it's probably good if I die at like near 0 so I can find my stuff. But anyway, let's put a bed. Let's make a bed here. I don't know why. I don't even know if I need spider eyes or anything. I think I've been getting rid of those. Or I was like freaking like 9 months ago. I don't even know. I played this like a year ago, man. Like whoever's watching this, you're probably like, what is this? Like episode 40 or like whatever this is. Like, what is this? Yeah, it's because I played it a long time ago, like a year ago. Okay, it wasn't that long. It's more my recent Minecraft experiences because I played Minecraft for like 3 years, and I played it a lot, like a lot, like a lot. Like I played so much Minecraft, you'd be sick. I like I gained weight, and I didn't do that well in school, and like yeah, that I dedicated probably way too much time playing Minecraft. Like I could, if I had spent all the time that I had been playing Minecraft doing homework, there's a good chance I would be working, like I would be working at Google right now, or some other like some other company paying me like 130 grand or something like that. Don't know if it would necessarily be the most fun job in the world, but um, or maybe even better. Who knows? Who knows what I could be doing right now? But it's not. But I haven't wasted all my time. I'm more of an inventor than just a steady worker, I think. I'm not the type of person who likes just doing the same old thing every day. Like I'll do it for a few months, but then I'll get bored of it, and if it's not like cutting edge, if I'm not and I don't mean by felicious, I don't mean like cutting edge, like just like the next type of phone thing or something. No, I'm talking legit. Like, you know who inspires me? Like Tesla inspires me because he invented the cell phone before anyone even had electricity. Like, people didn't even know what electricity was, and he was like, cell phones. Like the technical term for like the technology a cellular, like a wireless device uses, like is the exact same technical term that Tesla, like he's the one who came up with that term. Like like I know I say like a lot, but for reals, no joke. No joke. So, oh, what am I doing? I like made a bed here. Um I guess I'll just have it then in my inventory. What's up, sheep? Oh, I'm supposed to... What am I supposed to do? I'm supposed to like shear the sheep or something. Let me check. See, this is the problem. Is I have no idea if there's some kind of chest missing or something like that. I totally left everything behind. I do have all this, so it seems like I have a lot anyway, so it doesn't seem to matter too much. I don't know if I should keep the mycelium. Like it's like a rare, probably never get this again object. But it's not like I'm gonna. It's not. If I stick to the rules, I can't build a base. And if I can't build a base, I can't really use mycelium necessarily. I guess I can kind of wait in an area and let it grow and then like harvest it with silk touch or something, but and then I'll just have like a stack and I can keep like growing it and using it to make, I don't know, like spending the night places and growing mushrooms or something to make like, I don't need mushroom. I mean, I can make invisible potions. I don't know. Let's get rid of this. I remember, now I'm starting to remember, I used to get rid of stuff a lot. Like, a lot. Just, kind of just be like, nah, I don't need you. But yeah, we supposed to be like at a stack of wool from what I remember. I'm supposed to keep collecting wool until I have a stack just to make sure I never run out of beds. It's kind of like this rule that I have, like, if I have a stack of wool, then I know I'll have a bed. Yep, 54. 56. So, I don't know if I should... I wore a Microsoft shirt for the last couple days. I know it should have been just one day, but I slept over somewhere else and wasn't able to shower. And then I did gymnastics tonight, so I really stink. I definitely needed to shower at that point. So, what should I talk about? Microsoft? I never really told anyone this, but I actually... Well, I might have told someone, I don't know. But I actually applied to Microsoft, and they had the easiest interview question, like, in the world. It was so... Well, to me, it was easy. It's not actually, like, easy to everyone that I've told it to, but to me, it was, like, really easy. It was basically... how do you weigh 9 objects, given that you can just... Okay, given that you can weigh 9 groups of these 9 objects twice, and either... or 2 groups, I guess. Determine... Assuming that all of the objects are the same weight except one being heavier, determine the heavier object. And the solution... Well... Okay, pause it right now and try to think of the solution if you think you want to try to figure it out. Basically, you can weigh the groups of the objects twice. There's 9 objects, and you have to find the one that's different. Don't find the one that's heavier. So yeah. Anyway, the solution is, and I figured this out really quickly. I think I had to like write it down on paper or something, and it was, well, I don't think, I know that I wrote like a picture or something on paper, but basically the solution is you weigh 3 groups against 3 groups, and then, or sorry, not 3 groups. You weigh 3 objects. You separate everything into 3 groups that are each have 3 objects. You weigh 2 of the groups, and then that tells you whether they're the same or one's heavier. It tells you which group the heavier object's in. Then you take that group and you weigh its 3 objects by taking 2 of them and weighing them against each other. And if they're the same, then you would say the third object is the heavier one. Otherwise, the heavier one out of those 2. So it's kind of like an inductive problem. Like you can extend it. You can say like, oh, I want to weigh like 27 objects or whatever. You can weigh it 3 times and blah blah whatever. Who cares? It's an easy question. I'm technically a mathematician, not a computer scientist, or maybe I'm both. I don't know how to classify it, but for me it was like a kind of a no-brainer. I'm really good at algorithms. I even put this on my resume. I'm pretty sure that I scored like in the top 1/6 um, fraction of my algorithms course at University of Illinois, which is one of the best universities for computer science in the world. So like I know and I've learned my algorithms pretty well. Um, I understand these concepts actually very well from what I found out compared to the the average person. Now, when it comes to systems programming and stuff like that, and experience and specific things, I don't think that I'm that great. I don't think I'm great at like learning all those types of things. And I might have mentioned that I definitely wanted them to know, like, if they really wanted, like, someone who's just going to do system stuff all day long. Of course, I don't want them to hire me for that because I, I just don't feel like that would be a good match. But I still, I told them about Minecraft, and I tried to explain, a design that I had for a game that, it's definitely the point is to make something different and better, not like a copycat game. Like it would, I tell people about my ideas, and some people just try to classify it and be like, "Oh, you're trying to copy." No, 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 no. That's like saying that right when a 3D game comes out, being like, "Oh, I want to make a 3D game." Oh, you're just trying to copy Zelda or Super Mario 64. No, I'm not. It's a 3D game, but it doesn't mean I'm copying it. Just like if I say I'm making something that's voxels, doesn't even that doesn't even mean that my voxels are cubes, and they actually are not. So, by the way, that's not even the same. So it's not even a cube game, but that's beyond the point. And it's also not the most. It's also not an important aspect to the game. The important aspect is that it has a fractal loading system, which I don't want to explain because I don't want to give like it's very simple and very well known and where like the method to do this. But for people to put the two and two together, I think that's where the innovation comes in, and that's where I want to protect my intellectual property and be like, well, I don't want to give away all my secrets and everything because they don't obviously if they because they ended up basically what happened was they ended up rejecting after I think the phone interview that I had, but couldn't explain why or anything like that. Now there was another part of the phone interview which might have came off as a negative thing, which I'm not sure, but they basically asked me how I tested for a certain project that I mentioned that they were asking me about. So the lady on the phone, she didn't really know too much technically. I'm not totally sure. She kind of said she knew some technical stuff, but then she was asking me about like testing and things like that. So test-driven development, basically, so most people, even computer scientists, so most even computer science, even computer science professors will tell you, test-driven development is, how you do things. It's how industry works. It's how it's necessary. All this other stuff. So, so that is kind of a sensitive topic for me. Not like I'm gonna get emotionally like about her, but it's kind of like something that I'm going to I can ramble on. I can like you can get me started on it basically. So I don't think that test driven development or testing code is a good way to design. And that being said, it it actually depend. I would agree that it depends on the language. It can be good depending on what your situation is. So so my claim is the world. So my claim is there's a lot of bias that I notice in people's beliefs and their understanding of computer science. And my claim is that most likely you, just being a random person listening, have one of these biases. One of the biases is that you think that anything can be hacked into, and that is completely that there's absolutely no support for it. The only thing that is like a statistical correlation to how our industry develops technology, and there's absolutely the mathematics says the exact opposite of that. So first of all, that's not even true, but we're not going to get into that. So it's definitely easy. It's not even just possible. It's actually easy to make something that can't be hacked into, but or that has no security flaws and things like that. It's not necessarily easy to make, competitive products on the market with those properties, but it is easy to actually make a product with those properties. It just might not get you a lot of money, and it might not be like a cutting edge thing. And because of just how economy works and how companies and blah blah blah, all these other things work, is things will have security issues because there is a lot of flaws and there's a lot of garbage in the system. That's basically it. It's not that it's not possible or that it's not even feasible. It's just that statistically, and given how our current state of the world works, and given people's understandings of things and how people develop things and how, yeah, people are not, yeah, people don't do things in a disciplined way. They do them in a way that gets them the most money, gets them their paycheck so they can go home and feed their family. And that's how programmers work too. And programmers can be very lazy even when they shouldn't. But the bias that I'm going to talk about is the test-driven development. So, yes, we're going to call it TDD for short, test-driven development. TDD is important if given that you have, let's say, a language like C++ or Java or C, and you are developing something that you know needs to work, and you are developing it very quickly, and you don't have any other tools that can assist you in developing it. And let's see what else. And you kind of have a design, but the design doesn't clearly prove that the implementation of this design, or it doesn't clearly give you a perfect implementation. You can't convert it easily to an implementation perfectly without any flaws. And sadly, that's most of the time that's actually the case in practice. So in industry, that's what people do is they'll use, I don't know why I'm going south because I'm at 73. I should be going along 0 I don't know, but I have been heading east. So anyway, this is good that I'm talking because it's just distracting me from my boring heading eastness. And usually I'm talking about what I'm playing and what I'm planning to do, which is kind of boring. So, because it's just Minecraft and who cares? So, yeah, test-driven TDD is not necessarily the best thing in the world. It seems like you can make a cool system for doing it, and it seems like you can be like, oh, this is a good, TDD like this, and then you create your test cases and you try to, design your code to kind of fill those test cases. That kind of makes sense but that's really, to be honest, that's actually kind of old school. That came out of that was naturally born out of a system where it was kind of necessary to do that. But, and this isn't a sad thing, this is pretty exciting. saying that test-driven development is like unnecessary is actually a pretty awesome thing, and it should actually get you excited because like it's actually really cool that you can create programs knowing that they work perfectly without testing them a bit. And not on top of that is you know that it works better than something that has been tested because you know that the thing that has been tested might not have actually been tested properly and to the full and fully. And so the way it works is it basically works as, oh, okay, I don't want to die here, so let's. So most people don't realize this, but programming languages are actually from built by people who are basically mathematicians. And one thing that you call an empty set is null. You would say, oh, if a set's empty, then we call it null. So programming languages actually have there's been a lot of design for them to actually have these properties which are specifically like they're actually very intelligent properties. They allow you to prove things about your code essentially. They're basically it's the same as a proof. In fact, there's a theorem called the Curry-Howard isomorphism which basically says that a typed language, like a typed computer program that compiles or is verified, basically is the same as a proof, the same as a mathematical proof, because each type, when it's compiled, it basically says that that type is inhabited by something, which means essentially what it means is that it's like there's a set that's not null. And because it's not null, like you know that all your branches will do something, all your branches will return a value that makes sense. It doesn't necessarily like prove all possible like logical things about your code, and I'll get into this in a minute, but it does, there's a lot of things proven at this point, and these things are it's very good to know these things that are proven. It's very helpful. In fact, it's so helpful that you can use and abuse it to the point where you basically don't need to use tests and test-driven development. I'm not going to say this in an absolute sense right now, because I'm going to get into like this another topic in a second, relating to, I guess I'm just going to call it combinatorics. But basically, when you use the type system, it's kind of like graph theory, or you could call it type theory. And there's also there's something called category theory, which gives you kind of like this weird, like this interesting tree structure of types. But to me, like they're all related. Was I going east? Well, I'm going east now, whatever. They're all related. And I would say that those basically, the way they work is they allow you to create a language that separates things. That's basically what it does. You can name two different things. They're two different types of expressions. They have different names. You called them different things. One is not the same as the other. But you know that when you have an expression, it's going to be like one or the other. So then they kind of have this thing in common, like they're both expressions or something like that. So, and this is kind of like wishy-washy, abstract, but basically, I'll give a hard example of this in a second. But the idea is You can prove, like, you can prove that your expressions all have types. You can prove this kind of the structure, and you can prove that it's correct, which is awesome. It's pretty cool. And it proves things about your code, like it won't crash or something, because you crashing means that it would need to reach some exception state, and if there's no exception state, or if it's, then it just won't, can't do that. And even exceptions can be actually built into your language. Like you can have something that basically into the type language. I don't mean like you throw an exception and it treats, and that means it crashes. I mean like the exception is actually like another logic control part of the grammar that basically what it does is it the only special thing about it is that it instead of the fact that it can just jump up one expression in the stack, it can jump up more than one. Like it can jump up a whole bunch of them. And but it's still deterministic, it's still like very understandable of where for example, if you're searching in like a tree, you can have an exception once it finds something, and then that goes back to like the start of the search algorithm or to the end of the search algorithm. And that's faster than writing a search algorithm that once it finds something, then it says, oh, well, I found it, so I'm just going to mark this Boolean, or I'm going to, decide to return this all the way up the stack, or, you know what I mean? It's either could keep searching or could try to return up all these like branches that went down. When, if you have an exception, you can just jump back basically. And there's something called tail recursion that kind of does this with lists or with yeah, but even recursion itself has issues with safety, and you can actually you can skip a lot of things in Java. You can actually write safe code in Java, like take advantage of the type system, but you have to like get throw out a whole bunch of stuff. You have to throw out nulls, you have to throw out recursion, you have to throw out a whole bunch of junk, and just not use all that stuff. And if you don't use all that stuff, you can actually have a thing. There's a guy who programmed this thing. You can look him up. Look up the Incredible Proof Machine. I'll say that one more time. The Incredible Proof Machine. Now that's different. I'm not talking about the Incredible Machine. I'm talking about the Incredible Proof Machine. There's a website. It's a free. Try the game. Try just doing the first level. Basically, you just create a proof using blocks. And the guy who made it, look at his GitHub. Look at his website. He talks about. He actually mentions like rewriting some of his code in Java if you want to do that. And he says you can't use nulls and blah 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 and all these other things because he wants it to be a clean, provable construction. Now, what am I getting at here? So what's going on? So basically the point is you can write code. Like you can write game. Look at Minecraft. Like you can write all sorts of stuff in Java and C++ and all these like languages and stuff, and it's fine. Works out great and everything. And sometimes there's bugs here and there, and you have to fix them, and doesn't seem like too big of a deal, right? Well, the problem comes in with this type of development is when the project gets really large, really complicated, and also I want to mention that, like, make sure that I mention this, and also you're making changes to it a lot. You're using it a lot, you're abusing it a lot, you're updating it, and you're changing things around, and you're designing it as you go. You don't just design it and then build it and then you're done. You actually design, build, and you don't stop. Like it's a mutable thing, and this doesn't really exist yet. But imagine coding and using the same software at the same time. Now, it might not sound like it makes sense, but that is that actually does make sense. Um, in theory, you can definitely like do stuff like that. It's really cool. But yeah, files, object oriented, all this stuff um, are machine abstractions, and they're not very good mathematically. They're not very like sound things. They actually weren't even intended. They weren't even the original theory of computation. Like the original theory of computation was not Turing machines. Like people think of those that as like the first computer and things like that. It's definitely not. The first form of this was kind of between Church and Gödel. So Gödel did a proof of the incompleteness theorem, and it was basically just like showing, logics. It was basically just like logic, like classical logic, intuitionistic logic, grammars, things like that. Church was Turing's advisor at Princeton University in the 1930s. He came up with something called the lambda calculus. It is a significantly more is a different model of computation than the Turing machine. It's less obviously it's less machiney and more expressiony. Just think of it like that. It's expressions, but it's a computer. It's a computer model. Um, it's a computer represented. It's basically computation represented with expressions. So it's kind of between math and computer in a way. Um, I don't know a better way to. It's isomorphic, so it's the same as in power, in representability as a Turing machine. So you can write the same kind of programs you write in a Turing machine, you can write in this, and vice versa. They're exactly the same power. There's nothing one can do that the other can't do. If one can take a square root of something, then the other can. If one cannot, solve a certain problem because it's undecidable, then the other one also cannot. Why do I know this for sure as a fact? Like, this is a hard fact. This is so proven 100% true. There is no flaw in this. There's no guess in this. There's no statistics in this. This is like 100% absolute. Why? Because there's a proof. And what's the proof? Well, the proof is that one has been reduced. Each one has been reduced to the other. What does reduced mean? It means that each one. It means that it's been simulated by the other. So every aspect to a Turing machine, moving right, moving left, writing on the tape, whatever, can be mapped to a type of function in lambda calculus, which then can then, since it represents that functionality, any type of Turing machine that exists can be represented in lambda calculus, and its functionality can be like simulated essentially in lambda calculus. The same goes the other way around. It goes both ways. And that's a proof of equivalence. That's a proof of isomorphism. So I'll just put it this way. When it comes to languages that exist and have flaws, they do not follow these like really nice inductive properties that lambda calculus kind of provided. And so you have like these nerdy people saying like, oh, we should use Haskell or these like more, sophisticated languages somehow, and other people are like, what? I can't even like, print a line, so I'm going to use Java and C. And so you got this crazy like thing going on that's a mess, and it seems like a lot of people don't know what's going on. So I want to try to explain what's going on because I have like this understanding of kind of a lot of what's going on, and at a high kind of level. and it's not just like I just have this understanding because I looked at it and I'm thinking, oh well, I think I know what's going on. No, no, no. Like, this is what I've studied. This is what I've studied um, when I wasn't playing Minecraft. This is something. This is one of those things that I studied when I was. I need to go east. When I wasn't playing Minecraft. Um, so so nulls, like no, just nulls themselves are okay. It's fine to represent a set that's empty. That's okay. However, however, when writing a computer program, using a typed language, using a statically typed, what's commonly used today, um, you don't want nulls to be at the level. You don't want types to be empty, but you can still represent an empty. You can still, that doesn't mean you can't represent an empty set. That doesn't mean you can't emulate an empty set. So in Haskell, there's something called a list. A list can have a sublist, basically, another list of the same type, or you can have an empty list. And the empty list kind of acts as like a null. It kind of says, okay, stop here, there's nothing here. And when you branch on something, a branch is basically like an if. Like, if this, do that, if else, do that. But it's more sophisticated. So an if only just kind of implies that your branch is a true or false. But really, true or false is just like a binary kind of, like, it basically means you have two options. But there's actually a lot of cases where you can have more than two options. You can have three or four, or it basically depends on the type. So you can have a type, and then you can branch on whatever the type is, whatever its like subtype is. So for example, you could have like an animal, and you could say, well, if it's a chicken, do this, and if it's a cow, do that. But this is the thing, you know for a fact, 100%, that when you reach when that code is used, you know that there's an animal. Like, there's no doubt. There's no way it's gonna do this. Like, this code is not gonna work. It's not even gonna reach this part of the code or whatever. This part of the parse tree, unless this animal exists. And what that means is that you know that means that like your code just works, because the only thing it can do is what the expressions allow to. And the problem with Java and C++ and C is they have these nulls that are not like these empty list types. They're not like a none animal. Like, you should be able to have an animal, and then an animal could be a cat or a dog or a none. And then even if it's a none, you could, I guess that means it's not technically it's not an animal, but it's still of an animal type, and so you can still branch it. You can still say like, oh, if it's a none, do this. It's still not gonna like crash or do something weird. But Java and C++ is very have this really bad thing where basically if something's not like expected to be null, like if you write the code, like you can actually write code. You can say like animal, or like, yeah, you can say, this animal dot, get eyes or something. And if it's not actually an animal, like if it's null, if there's no object there, if it's the empty set, not a typed empty set, but if it's like null, like as in it's built into the actual language, not into your type. but the language itself allows you to set that thing to either be a type or to null, like a globally used kind of value, or a value that's used kind of at the meta, at the system, at a level like below the type system. Like before it even checks to see if it's going to use types at all, it's like, well, let's just make sure, it's not null first. It's like, no, 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 no. That's horrible. That breaks the whole point of the type system in the first place. The whole point of the type system is to prove that your code isn't going to crash or is not going to do anything. It doesn't prove everything about your code. I'm not going to say that, okay? But there are ways to use it to prove more things about your code. But that's how it does it. It does it by proving that these types are inhabited, that these expressions have values. Because the way propositional logic works, like when you try to prove something to someone and you have an expression, these expressions, when you prove something about a set, for example, you have to actually prove two statements, not just one. So the two statements are, first of all, that an expression or an element exists, or the set there's an element of the set that exists, basically. And then the second thing you're proving is that proposition, that expression, that element, whatever, has a certain property, or that it's true. Basically, true can be considered a property, but basically you're saying you're actually proving not that something exists, but you're basically not proving that something's true. You're basically proving that assuming this thing exists, it is true. So you're proving this implication. You're proving an if-then. You're proving that an if-then is true. So you're basically saying, if this proposition, if the set exists, then it is true. But that doesn't actually prove that it exists. That's why proving it exists is a separate thing. So when you create a typed program, it's really nice because it's set up for you to both prove the value of something and that it exists, both at the same time. And this is called intuitionistic logic. It's an actual formal logic. So logic is it's not like this wishy-washy term that says like, oh, logic is how you think or something like that. No, it's a thing. It's an actual grammar. You can look it up. There's exact specific rules to it. You follow the exact specific rules, and you'll notice that it's a different thing than classical logic. It is less powerful, and by less powerful, I actually mean a specific thing. I don't mean like, oh, it's not used as much or something. No, it's less powerful, which means it has less expressions that you can make. So it's less powerful, meaning it has less expressions. By less expressions, I mean if you try to map the number, like the expressions from one to the other, you would notice that you can map all the intuitionistic ones to the classical logic ones, but you cannot map it the other way as well. So being less powerful doesn't mean it's worse. It's actually better. It's actually more. So now I'm talking in a sense of just, usefulness. In that sense, it's more powerful. In that sense, it's more useful. So it's funny because it's less powerful, it's more powerful. So yeah, because formally it's less powerful, intrinsically it is more intrinsically powerful. So it has more, it's cleaner, it's easier to prove things with it. Um, and I don't mean that in like I don't mean that second powerful in it like an exact sense. I don't mean it in a hard sense. They're both actually useful, you but one of them but you want to take advantage of the one that you want to take advantage of the one that you're using basically to do the thing. And so basically, and so I've talked with people about this, and somebody said, and I kind of agree with this, but I don't like it. But it basically, my friend said, oh well, and he's a genius. My friend's a genius. But he kind of said, we talked about this. I talked about it with my boss, and I think languages are, you know, they should be what they represent what they are used for, or they're designed to be the best for what they're needed for. And that's true, but I feel like it's like an extremely mislead. Like I feel like most people are going to like misunderstand exactly how they should understand that. So most people, I fear that they would think that, oh, well, every language, tons of different languages are good for different things. So if I want to do this, I should use Java. If I want to use that, I should use HTML. If I use this, and blah blah blah. Um, and that's that. I don't think that I don't agree with that. So I agree that his statement is technically true, but I don't agree with like the general like consent, like the general understanding of that statement. I don't think that um first of all, his statement does not imply that there is not a master language to govern them all. His statement does not imply that there cannot be a there cannot be a best language. So I'm still arguing that we still haven't proven that it is still possible that there is a master language that is strictly better than other languages. Um, and some people will think like, what? But if it depends on what your thing is, right? If the master language is better than all other languages at all tasks, then his statement would hold. Um, Now I'm not going to claim that yet, but I am going to claim that I have an idea for a so-called language, except that it's not precisely, and I can't get out of this. Oh, shift. That's why. So I don't have a, so I'm probably not going to get into this too much, but it's not a programming, there's a difference between a programming language and a formal language, and the ideas of them. So a formal language is literally a set of strings, could be infinite, and that's it. It's a set of strings. And when you code using text, you have a tool, usually when you're coding like programming language of some sort, you have a tool that lexes and then parses and then verifies and compiles. And it verifies, it's supposed to, they usually don't, but it's supposed to see if that string is in the language. But they're usually not perfectly accurate. And I'm going to get into why perfectly accurate does actually matter in the long run, or in it will matter. Like, it is possible to make programs and stuff where it doesn't matter, sure, but and that's done all the time, sure, but it does, in the long run, like it the whole point, it will matter. Okay, so here we go. So yeah, it's possible to have crappy programs that just avoid their buggy code. It doesn't matter. The point is, a language. I'm not even interested in the language itself. Because if you have to lex and then parse it, that's different than a parse tree, which, yes, you can represent it with a language, but the parse tree itself, instead of looking at the string symbols and saying that they're computationally complete or something, or the language itself can support something Turing complete. But you can look at the grammar and see if that does it. Which is nicer because you can work with inductive properties of grammar better than you can with a which is a set of symbols or a set of strings. So this conversation is getting so long, or this, I'm giving everybody a lecture. So you can actually make a parse tree which doesn't necessarily represent exactly what the computer is doing, but it represents something else. And so technically, there's a language out there, and it's actually a language that Microsoft made. And it's a language that is the symbol for my YouTube channel. It's called Haskell. Haskell actually has this property, and most people, I don't think they realize this, but Haskell, the language or the grammar, does not tell the computer what to do. It doesn't tell the computer what to do. It's not a set of instructions that says, computer, do this. What it is these expressions that have these really clean, nice properties that you can have an algorithm that evaluates them and determines their values. And it can evaluate them in different orders, and it doesn't really matter because they're very clean and they're called pure functional. And that's not necessarily instructions for what the computer does, but you can kind of guess what the computer is going to do, or what the computer would do to try to figure out like how to evaluate these expressions. But the reason why it says it doesn't actually tell the computer what to do is because there's actually stuff. If you just use the Haskell language by itself, you actually can't even use inputs and outputs. And yet when people run Haskell programs, they're doing inputs and outputs. So how can that be? Well, it's because they're actually using more than just Haskell. They're using more code. And that more code might be actually legally called Haskell or something. I don't know. You might be called Haskell in some sense, but it's not part of the actual. It's not part of the pure functional grammar. It is extra code that is attached to a program when you actually write the program that tells the computer what to do. And by the way, the program is a mix of something that you write and something that the interpreter does. So it's actually two different levels. But when you write your expressions, that's not as specific instructions, but it will kind of guide what the computer is doing through the interpreter or through the what the compiler kind of creates. But you also can attach things that are direct statements and are direct things, and they're called actions in Haskell. And these actions are actual actions. They're actually instructions for the machine. And the reason why that needs to be separate is because for Haskell to have these nice properties of being purely functional, it needs to be intuitionistic. It needs to be less powerful. Less powerful as in it does not have the Turing complete power. So why would you want something less powerful? Well, because it has these nice properties, these nice provable properties. Well, why do you need these provable properties? So many people write software without them. Yes, they do. And these software programs have a lot of bugs, but these bugs can be managed. That is true, up to a certain point, until you have very extremely large programs, and it's not just up to a point, and then once you reach the point, it becomes a problem. No. The problem exists, but it grows, and it biases how development is done. It doesn't just make it harder to develop. It biases and it changes how people develop software, and it makes people do things that are very bad. For example, rewriting things that have been written. Theoretically, all of society, all of mankind, should only have to write an algorithm once. Never rewrite it in code again. Never write it in another language. Never have to rewrite it in multiple, like Java, and then assembly, then some other, and then Haskell, and then some other. No. Theoretically, an algorithm or a library can be written one time and then used forever by many different people, by many different companies, without issues, and never will that have to be seen again. It's basically like a theorem in math. If you have a theorem that's proved, does anyone else have to prove it again? Once you prove a theorem, like once Fermat's last theorem was proven, is there anyone who's going to get the credit for like reproving it? Ever. They might make a faster or a shorter proof or something of the sort. But to use the proof itself, like the properties of the proof, like the fact that the end result of the proof, which is, that it's true or that it's false or something like that, is anyone going to have to figure that out again? The answer is no. No, it's done. The information is there. The expressions are there. The proof exists, and it's there. So, what about programs? Well, same thing with programs. You can write something once, and it doesn't have. This is the thing. People think languages. They think that languages are something that you build on. And yes, that is so traditionally how it works. But I foresee that just completely changing. And the reason is because type languages, first of all, classical type languages, classical type theory is a specific way of going about writing a program. I'm just mentioning that. It's specific and it's traditional. It is possible to do things another way. And another way to do things is to make something called dynamic types, which means using a type system that inductively can define itself. So instead of just one layer of types, it's an unbounded layer of types. Now there's some self-similarity to it, and the self-similarity kind of is limited to like functions, or to basically saying that like functions can exist, basically. But everything other than that, basically, if you have an expression that defines what a type can be, those expressions are made up of these values, of these other types. And those themselves can have their own meta types, their own types. That's one level up. And then those can be defined, and those can have types that define them. So it sounds kind of silly. It sounds kind of like, wait, what's going on? And yes, that's how cool it is. That's how fractals work. That's how induction works. This is how math works. This is what makes math cool. This is how computer science works, through inductive properties. And now I'm saying that this is how type systems can work too. They kind of already work like this, in one sense. They work in the sense that types can be constructed inductively. So type can be made up of subtypes, and you can combine them, and you can do things like that. But what I'm saying is you can also have a type for the things that define a type in the first place, and so on. And once you do this, you realize that the lines between compilation, or interpreting a language, or dealing with a language at the type level, and then dealing with a language at the execution or the value level, are sort of similar and don't necessarily have to be the only two steps. There can be a step between all the type levels, and each one kind of looks like compilation to the one before it, and it looks like the one after it, and it looks like execution to the one before it. So you can be messing around with this computer program that, who knows if you're editing it or if you're running it and messing with it as a user, but you're changing states on it. You're changing its state. And in one sense, you're using the program, like you're running it. Like you're literally running the program and using it as if you compiled and executed an end product. But at the same time, you're also editing it and you're changing it. And yeah, it feels like I'm explaining like special relativity to people. It's basically like telling them like, by the way, time is not constant. So I'm basically saying like, by the way, compilation is not constant. It's hard to explain, but the point is, there's a way we've been doing things traditionally, and don't get your head stuck in it thinking that this is how things are done. It's not necessarily how things are done. It is not the only way for things to be done. So I researched that. I had to figure it out because I was trying to make a compiler thing for Haskell, and I realized that there's something interesting going on with the I/O, and I had to figure out what it was, and I couldn't wrap my head around how the I/O actually did. I just couldn't understand if it was truly purely functional. It just didn't make sense. It just didn't make sense that it could do any form of input and output. And then I realized the lie. I realized the trick. And it reminds me of this puzzle that I saw when I was younger. It said, where is this piece missing of the triangle? And I realized that it was not a triangle in the first place. And so I realized the lie, the trick. So I was correct that you couldn't do inputs and outputs with a pure functional language. But they lie to you. And when you run Haskell code programs, main programs, you're not only running pure functional Haskell. You're also running this extra stuff on the side. There's extra stuff going on. And it is not Haskell language. It's not the pure functional language. It is an extra thing. It is an extra, there's extra code. I don't know how to explain this very well. I keep saying extra because no one ever said this. No one ever made this clear. People just kind of think, oh, I don't get monads. I think I might get them, but no, something. Yeah, monads is how it interfaces with it. Monads is how to properly interface. It's basically just the proper, like if you want to speak to someone, how do you do it? Well, you walk up to them, you look at them in the eyes, you open your mouth and you say, "Hi, my name is blah. Let's talk about blah." And so you speak to them and you communicate. And if you didn't use your mouth, like if you tried to just itch them or if you tried to just smell them, it wouldn't work too well. So monads are like speaking. It's like, this is how you speak with, like, this is how functional programming works. Like, it passes functions around. If you want to communicate with it, you pass a function around in it, or you pass some kind of value that you pass things to it and it passes things back. It likes to pass. It's like football. It just passes and catches. That's what it does. Because it's functions. That's all it is. It's functions, pass parameters. Shoot, am I gonna die? Oh no, crap. No, 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 no. No, 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 no. I need food. I need food, I need food, I need food, I need food. Yes, cow. Come, cow. I can't die, I can't die, I can't die. There we go. Let's eat this food. I was stupid. Anyway, I can't believe I lectured about computer science this whole time. I'm so stupid. I was supposed to be playing Minecraft. Point is, there's something, when you run Haskell or some other language like this that does inputs and outputs, you write an interpreter and a compiler that does extra stuff. It doesn't just evaluate the language expressions, it does extra stuff. And this extra stuff is inputs and outputs and whatever you want. It can be anything you want. It can be messy, it can be crappy, it can be whatever. Just, there's no rules to it. Just imagine it can write, graffiti anywhere it wants. Except for the language. Like, it actually doesn't mess with the language, but it can mess with your computer, it can say hi, it can whatever. Okay. So this code just does all sorts of stuff, and it doesn't even, it communicates in it with the outside world, and it says things to your operating system, and it says things to your GUI or whatever, and it communicates with things, and it's not purely functional. It's just like, imagine it works like C, kind of. It just kind of does stuff, and it's useful. And it talks to the machine. It's designed, it's like, maybe it's even a language that's specifically designed for the machine that's running it on. It's instructions for the machine. So imagine that attached in its own little like capsule or something, and it's organized. It's kind of like put into like these little packets, and it's just like, okay, well, you're like this little capsule that, well, I'll kind of treat you like a function or something, or I'll treat you like a like a thing that when I run you, you say hi or something like that. I kind of organize you a little bit and I give you a name or something like that. Then I pass you in to a Haskell function, or I pass a value that I have in my Haskell function to you, and you do something with it. Like you print hi if I pass you hi or something. So it does the things that needs to be done. It does these things, but the Haskell functions, they don't look at it. They don't care. They don't pay attention to it. They're like, okay, you do your thing. We have nothing to do with you. They're basically like these. Think of them since functional programmers are all picky and everything. Think of them as like these snobby little, like, oh, I'm not gonna touch that input output. You do it. I'm too snobby and rich. So just think of them like that. Just think of them like snobby, because I think that's how people view functional programmers. Like, I think they think that they're snobby and they want everything to be perfect somehow, which is funny. I like this. I just think it's funny to laugh at stereotypes and be like, yeah. From their perspective, that might be what it seems like. Of course, I would disagree with the truth of it, but that's because I feel like there's something. I feel like there's an intrinsic truth behind why these things are necessary and what's good about them. And so it's more of a joke. It's more of like they'll pick on you because they know that you're smart. They know that you kind of know what you're talking about, but they're like, well, I'm just going to pick on you anyway. I'm going to tell you what I think either way. And then you prove yourself. So that's how people kind of react. And that's exactly what they're going to do. They're going to prove themselves because they like proofs. Functional programmers love proofs. That's what they're all about. So I'm not like a good functional programmer or anything like that. I'm not that great at this kind of stuff. I just like the theory. I'm more of a mathematician than anything. And I even suck at math too, so don't even call me a mathematician. Just call me a crazy set, like something. Okay. I've talked my throat dry. And I've headed east. And I'm at Buck like 1,000. Okay, I need to go to sleep. I will see you guys. Thanks for watching. I don't even know how long that was. I don't even know what episode it is. Let me share a secret with you. I'm going to be working on something very interesting. Well, it's not very secret because I kind of mentioned it to a lot of people, but there's this program called Agda, AGDA. You can actually run it in if you have the Haskell tools, you can kind of get a hold of it, but the language is nice. The language is intuitionistic. It's dependently typed. It has this infinite tree that I was talking about. Haskell does not. Agda provides a nice structure for things. And I want to design a software. I want to design software. I want to make software development easier in the future. And by easier, I mean create a technology that in the future, it might not increase technology tenfold now, but in the future, it will allow for technology to be increased tenfold, 100-fold, 1,000-fold, a millionfold, etc., depending on the size of the software project, because the whole point of it is scalability. And somebody, somehow, some way, will have to design a structure to work like this in order to get this type of scalability. Now, this scalability is not a global optimum. It's not like, oh, use this to design a perfect, you know, um, NP complete type perfect software algorithm for this problem. No, 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 it's not that. You don't use this to design NP complete perfect things. That's for like either God to do or for like super massive computers the size of the sun to do, or for like some crazy interdimensional, who knows who's going to do that, but it's not going to be normal computers. But with normal computers, you can make something scalable. You can make something designed to be super, super scalable. Um, Super scalable. And that's kind of the point. That's kind of the thing. That's kind of what I'm trying to get at. What I'm trying to do is and whenever you develop new technologies, you're basically automating something for someone. Regardless of how you think of it, you're automating something for someone. Somehow you are automating something in some way or not. Even if it's like a workout machine. It's like, what? You're making something that makes someone do work. How are you automating things you automated like the process for them. You automated like if it's like a treadmill, look, you just automated like a ground for them to like move on, right? You like automated like a track so they don't have to like go somewhere. You automated like the dis their positioning. Their positioning on like on like a running track basically. There's an automation in any kind of technology development in some way or another. And so what I'm trying to do is I'm trying to actually automate deve- um, not all of development, but the costly manual algorithms, the costly um, repetitive kind of algorithms in development. And they sound trivial because it's basically like, oh, if you can match these types together, you can program. Oh, okay, so what am I going to automate there? Well, the matching of types. But that's easy. Not necessarily. Trust me, there are programs, and I've worked with an actual program before, an actual software project in F Sharp that was very complex and had large expressions for types, and it was difficult to manually get them to match up. It was difficult. So to automate the restricting of what matches are viable and which ones are not would actually be very helpful, because otherwise you just have non-determinism and you have to enter different characters and you don't really know what you're doing. So this doesn't necessarily change technology instantly by tenfold, because somebody made like this conjecture that nobody can change technology by tenfold, and I'm not exactly like claiming to do that, but I'm saying that this technology will eventually like be necessary for like a tenfold improvement over like time in the future. So I'm not claiming to go against that kind of conjecture or that theorem, because I think that conjecture or that idea was that somebody can't just come up with a technology that like changes technology instantly tenfold. And I guess I would agree with that. That makes sense. Um, I don't know if it's really you can't really prove it, but anyway, thanks for listening. This has been Tim, heading east in Minecraft, but mainly talking to you about math and computer science. I will see you guys later. Have a nice day.